Good afternoon, friends. We are back again to another class of linear algebra. Linear algebra is actually a huge subject, beautiful subject, but needs time to go through it. At this moment, to start with, I am introducing a concept which I have already spoken in the last chapters, last classes, but I am again reasserting that the notion of coordinates of a given vector of a vector space. Coordinate means a series of ordered series of real or complex numbers, means that if you have a vector space V which is a finite dimensional, of course we are just talking about finite dimensional spaces, then every V there given a basis B, every V corresponding to every V there is a coordinate. Suppose V is a real vector space and it is n dimensional, then given any V of that vector space, element of the vector space, then that V has a corresponding element in Rn. It is another way of stating that real vector spaces are essentially Rn. You can define a bijective mapping between them. So, what are those coordinates? What are those n real numbers, for example, which will give the corresponding coordinate of V in Rn, right? So, this comes from the basis. So, if say V1, V2, Vn is a basis of the vector space V, then there must be scalars alpha 1, alpha 2, alpha n such that V is the linear combination of alpha I and Vi's, that is alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. These scalars are called the coordinate of the vector V with respect to this. More compactly we can write this. So, I think I missed writing here, I should write here Rn or Cn, because I have not specifically said that this vector space V is a real vector space or complex vector space. So, every finite dimensional real vector space is related to Rn. They are structurally the same, there is a bijective map. Similarly, every finite dimensional complex vector space is related to Cn because of this fact. Now, once you keep this in mind, this is a kind of bookkeeping that you are keeping in mind. Every time you have a vector space which is finite dimensional, you take any vector V, immediately you should know that there is a corresponding element in Rn or Cn which is related to it, and that link is done through this basis, the representation through the basis elements. I would like to wonder, for you to take a little bit time and wonder about why should I call them coordinates, how do they relate to Rn, what makes them so important. That is something you have to really talk about. Can you tell me why you want to call this alpha 1, alpha 2, alpha n as coordinates? What makes, is there any motivation behind this definition? I will not give you the motivation, maybe you can talk to me in the discussion hour as what could be the motivation of calling those as coordinates, or is it just the definition? Of course, even if there is a definition, there is a motivation. So, what is that motivation that I want you to think about? You can carry on it as a definition, but what is that motivation? That is very important. Now, let us look at an example. The great mathematician Paul Halmos once said, examples, examples and only examples, because examples are the best way of understanding mathematics. He had huge contribution to algebra, linear algebra also, and had a very fantastic book, one of the first on linear algebra, called Finite Dimensional Vector Spaces. And of course, people do not use that book anymore, but it is a kind of a classic historical text on the modern aspects of linear algebra. this is not mu2, this is m2. I am writing a little calligraphic m. So, m2 is the set of all 2 by 2 real matrices. So, it is a real vector space. We now want to claim this set which consists of 4 matrices, because the basis elements must come from the same vector space. So, that this matrix, this collection of matrices consists of 4 vectors, and we want to say it is a basis of M2. So, it has to span M2, it has to also at the same time be linearly independent. So, these matrices are interesting. The first matrix is 1 0 0, second matrix is that 0 0 1 0, the third one is 0 1 0 0 0 0 0 1. So, what I have done is just replacing the first column. First I replaced, I had 1 all 0, then I had in the first column and second row 1 and all 0, and similarly henceforth. You see, you can write any ABCD here, any matrix here in this particular form, this linear combination, and this is so clear that if you just go by the definition of scalar multiplication of matrix, this matrix will finally become A 0 0, this will become 0 0 C 0, this will become 0 B 0 0, and this will become 0 0 0 D. So, if you add them up, it will give you ABCD. I do not have to really, I am sure all of you would understand this, and those who think who wouldn't find it difficult can obviously mail me. So, now what is, by the definition, what is the coordinate of the vector v, which is ABCD here? That is A, C, B, D. So, what we have done? We have taken the first column vector, put it at the beginning, second column vector and stacked it below. This is same, the coordinate is given by the vec operation, which we had learned earlier, vec class chapter, vec operation on B when we studied matrices. So, let us now go over to S2. So, now we know that this M2 has dimension 4. So, there are 4 elements in the basis which are linearly independent and spans the thing. So, it has dimension is 4. So, what about S2? So, the reader can demonstrate this that it is a subspace of M2, which I agree, and now what is the dimension of this? Now, you see now the matrices of the form A, C, C, D, that is here the first row second column vector is same as second row first column vector, A 1 2 is A 2 1. That is what is the definition of a 2 by 2 symmetric matrix is. Now, we want to claim that this 3 vectors 1 0 0 0, 0 1 1 0 and 0 0 0 1 are the basis elements of S2. Means we are essentially telling that this element, this S2 is actually a 3-dimensional space, and indeed it is, as you will see, indeed it will turn out to be. So, we will first show that these are linearly independent. So, you just add this up, putting the scalars alpha, beta, gamma, which are from R now, and that should give me the 0 matrix. So, when you finally do it, what I have is alpha, beta, beta, gamma, this is 0 0 0. So, if you match up, because these two matrices are equal, so all their elements are equal. So, means alpha equal to beta equal to gamma equal to 0. And you take any A, C, C, D, you can always write it up as a linear combination of 3 vectors, showing that the dimension of S2 is indeed 3. It is amazing actually. This can be done in n dimension also, this can be thought out in n dimension. So, you can talk about n cross n symmetric matrix, space of vector space of n cross n symmetric matrix, n cross n matrices. So, and then you can talk about n cross n symmetric matrices. So, n cross n matrix would have, that space would have dimension n square, while S n S n here, instead of 2 it is n, the space of n, when n cross n symmetric matrix, that will have dimension n into n plus 1 by 2, that you can figure out later. For example, here what happens here, n in that case was 2, that n cross n matrices, n was 2. So, here the dimension is n into n plus 1 by 2, because here n was 2, 2 into 2 plus 1 divided by 2, it is 3. So, that is the general formula, that if you have n space of n cross n symmetric matrices, then the dimension of that space is n into n plus 1 by 2. So, you have to have an understanding that this whole thing has to give me a number, right, that is very important. So, what happens, n into n plus 1 means n square plus 1, right. So, what would happen, or if you take n cross n matrices starting from n equal to 2, say, so it will have 2 square plus 1, that is sorry, n square plus n, n into n plus 1 means n square plus n. So, you will have, if you put 2 square plus 2, so it is 4 plus 2, 6 by 2 is 3. So, Sn in general can have odd dimensions. Suppose n is 3, so we will have 9 plus 3, 12 by 2, 6, again an even dimension. So, it depends on n. When n is even, so it is like n is 4, then it is 4 square plus 4, 6, 20 by 2, it is 10. So, it depends on the dimension that you are, n that you are choosing. So, it is n into n plus 1 by 2 would be the dimension of Sn. So, that is it. So, that is very important for people who work in optimization, but otherwise you need not. A simple example would give you an ample idea that for a subspace the dimension can be less. Even if it is actually a 2 cross 2 matrix, the space that it constitutes to become a vector space of the vector subspace of the bigger vector space, its dimension can be less. So, you see this now you can understand, these objects are matrices, I really do not understand the dimensions. Of course, we cannot visualize what is the meaning of dimension in this world of matrices, but this way, this algebraic way of defining things is the only way to bring geometric conceptions to a different category of things. The things that we understand intuitively in geometry, if those ideas have to be brought into other areas, other spaces, then there has been no way but to take an algebraic point of view, and that is exactly what is done through linear algebra, that you give precise definition of dimension through this notion of a basis in case of finite dimensions, and then as a result, for various spaces for which you do not have geometric intuition, you can still talk about dimensions. It might be surprising, actually. Ultimately, what is happening if you look at that? How many numbers were required, real numbers is required to express an element in M2? 4, dimension is 4. How many numbers is required to express an element in S2? 3, so dimension is 3. So, there is kind of, say, S2 is similar to, is isomorphic to R3. So, again that you can again go back to your geometric intuition, but if you just try to think about what is the meaning of dimension of a matrix, dimension of a matrix, dimension of a space of vector space of matrices, you cannot get geometric intuition unless you map it to actual geometrical spaces. So, this map, this bijection is telling you this dimensional property of R3 is the same dimensional property I will attach to S2, or R4 I attach to M2, that is it, that kind of thing. So, and that is why we have given that kind of definition, and because we have that powerful result that every basis of a finite dimensional vector space must have the same cardinality. Now, let us give an example of an infinite dimensional space. It may not be finite dimensional. So, what is the meaning of infinite dimensional space? That I will never get a spanning set which is finite. If I take a finite set and try to span elements, we will miss out some elements. Okay. Now, consider the space of polynomials of real variables, of course, of degree at most m. Okay. So, P of x, every element P in this set, Pm of R, of real coefficients and with real variables, real polynomials. It is not in the sense that it is not polynomial of more than one variable. So, I will talk about real polynomials, means I am talking about polynomials with one real variable, because you can have polynomials with more than one real variable, and that there is a whole fascinating subject of algebraic geometry which deals with solution sets of those kind of things, polynomials. Now, the question obviously that rises here is that what kind of space is PMR? Is it a vector space? Is it a finite dimensional vector space or not a finite dimensional vector space? So, given any p element of PMR, P should look like this when it. So, when I have a function, how do I recognize a function? A function can be only recognized by how it is acting on the variable, the input variable. That is the only way I can recognize a function, otherwise I do not recognize it. P is just an abstract thing, P is a polynomial. What is it? How does it operate? So, given any x real number, there will be coefficients a0, a1, a2, am, such that Px is a0 plus a1x plus a2x square plus amx x to the power m. If P has degree exactly m, then am cannot be equal to 0. It can have lesser degrees. Now, if I change the P, I call it some qx, then this a0, a1, a2 will all change. Now, I consider some functions, polynomials, which are actually called monomials, because they are parts of polynomials. So, this x, just x or x square or just 1 here, these are called monomials, M-O-N-O-M-I-A-L-S. So, polynomials are built using monomials, right, that is the idea. So, phi I construct polynomials. So, phi I x would be x to the power I to I is 0. So, in that case I will write phi when phi 0 x is equal to 1, that is what I should have written, and phi 1 x is x, phi 2 x is x square, I is 2, phi 3 x is x cube and so forth. And phi m x is x to the power m. Then the p, the functional p can now be expressed in terms of these phi 0, phi 1, phi m. So, any p can now be expressed in terms of these monomial functions, which are also polynomial functions of degree less than or equal to m. So, they are also in PMR. So, this p now, I am not writing x, when I write x you will finally get back this. So, I can now symbolically represent p as an object of PMR in this way. PMR is of course a vector space, because it is a subspace of the space of all continuous functions on R. Actually, it is subspace of all differentiable functions on R, because polynomials are infinitely differentiable. So, this is a spanning set, and we now claim that these functionals or functions, these polynomials or monomials form a basis of PMR. So, PMR is an m plus 1 dimensional space. And that is very important, right, to observe. So, if you look at it, what does it mean? This is true for any P I take in PMR. So, PMR is in the span of B. Now, is B forming a linearly independent set of vectors in PMR? That is the question. So, that is what we now investigate. So, let us look at this expression. A0 phi 0 plus A1 phi 1 plus AM phi m equal to 0. It does everything give me 0. So, what does it mean? It simply means for any z that I put. So, this is the 0 polynomial is equal to 0. This is not the normal number 0, this is a 0 polynomial. So, 0 polynomial is expressed in this form. So, 0 polynomial, when it acts on any x or any z in R, it would be of this form. So, A01, A1z, A2z, AMz to the power m, when I evaluate at any z, and the 0 when I evaluated at z is this. Now, what does it mean? When two polynomials are equal, which means that their corresponding coefficients of the powers of z are equal. So, here A0 is 0, A1 is 0, A2 is 0, and A3 is 0, and dot 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 AM is 0. So, which means these are linearly independent set of vectors in PMR. So, PMR is in the span is equal to span of these are linearly independent and hence forms a basis, and thus PMR has dimension m plus 1. Now, consider PR of all polynomials of any finite order, all possible orders are there. So, PR all real polynomials of one real variable and with real coefficients. What kind of space is this? It is an infinite dimensional space, because it does not matter that suppose you take this space again phi 0, phi 1, phi m, does it generate all elements of PR? No, because it does not generate an element like a monomial like z of m plus 1, it does not generate that, because there are no elements here that will generate it, this z m plus 1. So, you can P tilde is not, for example, is in the span of this. So, for any m that you choose, I can find a P tilde of the form z of m plus 1, which will not be in the span of this set. So, you can never get a finite spanning set, and these are the type of functions which span the polynomials, right, whose linear combinations are the polynomials of the space. So, you can never find a finite spanning set, and hence this is not finite dimensional. So, now using what we have discussed above, please try to prove that the space CAB or CR cannot be of finite dimensions and the space of all continuous functions on R. Now, let us try to answer the second question, that if I am given any set of linearly independent vectors and suppose I have just m linearly independent vectors and m is strictly less than m and n is the dimension of the vector space V, then can I extend or add few more vectors to the given set of vectors, so that the new set of vectors become a basis of V? That is the question that we answer, and when we do that, we will make a very important conclusion. The conclusion is that if I have an n dimensional vector space, then actually any set of n linearly independent vectors will form a basis. You do not have to really check whether it is spanning or whether it is not spanning, that just need not be checked. If you know you are on n dimensions, take any linearly independent set of vectors, you will do. So, if you are in 2 dimensions, just take any 2 vectors which does not have the angle 0 or 180 between them, that is it. That will form a basis. And this is a very key question. Once you understand, have a grip on this, you start understanding linear algebra much better. So, here is the result from Axler, which I will not prove because it is so simple, you can yourself do it. a set of vectors in Vn. So, is a characterization of basis is the basis of a finite dimensional vector space V if and only if every V can be uniquely written as this. And we have showed earlier that if you have a spanning set and if the spanning set just contains linearly independent vectors, then every element can be uniquely written. So, basically what it says that if there is a basis, then every element can be uniquely written. Basically, you combine the spanning set with linear independence, what we had earlier known, the same idea, same thing. So, I am just rewriting this so that you recall. The proof is here, but the proof is so simple, I will not do it in the class, and you can check it up in the proof. If you still feel that, oh gosh, this is just too heavy a proof, you can definitely ask me. Again, following Axler, we will move towards our goal, but we will move towards our goal in few steps. So, let V1 dot Vn be a set of vectors which span V. So, I have a spanning set of the vector space V. I do not know what it is, whether it is n dimensional or not. I have just taken n to be some number. Then we can reduce the set to the basis of V. It could be say n plus 30, does not matter. This n is some 30 times more than the actual dimension. So, dimension could be m, the actual dimension of V could be m and strictly less than n. Then we can throw away certain vectors, so that the final list that will remain will give me a basis of V. So, here again the process is pretty algorithmic, and let us see what it is actually. So, let B equal to V1, V2, Vn be the set of spanning vectors, and let us see that how Axler's algorithmic approach makes it a delightful way to move. So, if V1 is equal to 0, step 1, then you have to delete V1 because V1 is linearly independent. 0 cannot be a part of basis elements, right, because that immediately will make the whole set linearly dependent. Once 0 is there, the set cannot be linearly independent. So, if V1 equal to 0, throw away. So, in the step 2, what you will do? Step 2, you will see whether V2 is a span of V1, V2. Okay. If that is so, then remove V2 from B. Okay. Remove V2. So, if when I, so V1 is suppose not 0, you keep V1, then you are suppose you now take V2. So, V2 is say is in the span of V1, means its V1 and V2 are linearly dependent, then throw away V2 from that. Basically, you are throwing away some linear dependence, so that the final set would be linearly independent. Throw away, if not keep B unchanged. Now, suppose V1 is not equal to 0, you then try whether V2 and V1 are linearly independent. Suppose that is not also happening, then you come to V3. So, you keep both V1 and V2. So, you keep come to V3. Is V3 in the span of V1, V2? Is it related to V1, V2? Yes, then throw it out. And keep now, suppose you throw it out, now you have a new list V1, V2, V4 dot 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 dot, it goes on. Now, you have to take V4 and you have to check whether V4 is in the span of V1, V2, V3. Though you have thrown away V3, but you can still check whether it is in the span of V1, V2, V3. Then you again throw V4 away. So, then keep Vj from B, if not keep B unchanged, right. Basically, what you do is, I am making a mistake. So, if Vj is suppose V3 has been thrown off, now I will have V1, V2, V4. So, again check whether V1, V2 and V4, whether V1, V2, V4 form any linear dependent pair. V1, V2 doesn't form. Now check whether V2, now V3 is gone. So, just check with V1, V2 basically. So, if it is not, then because V3 has been already thrown out. So, in the new list I have V1, V2 and after that V4. Then again check. Suppose I keep now V4 and V4 is not in the span of V1, V2. So, I keep V1, V2 and V4 and then I go to V5 and then check whether V5 is in the span of V1, V2, V4. If so, throw away V5, if not keep V5 and move on to V6 in that way. So, in that way what would happen, the vectors that in the final original form, if you go by the linear independence lemma of the linear dependence lemma in the previous lecture, then the span of the original set of vectors and the span of the final set of vectors would be same. Okay. So, the final form of the original B also spans the vector space V, since the vectors that were discarded in the span were the remaining ones, right. They were so vectors that were discarded, they were already in the span of the remaining ones. So, the spans would anyway remain same, does not matter. Now, for the remaining vectors, none of them is in the span of the other vectors other than itself, that is obvious. So, none of them is in the span of the other vectors and hence by linear dependence lemma, the final set of vectors remaining in V cannot be linearly dependent, right. So, that is the meaning of that, then only you can apply the linear dependence lemma, that if none of them span, what is the meaning of linear dependence lemma? If you take out linear, if you just go and see your linear dependence lemma, you must find Vj which must be an element of the span of V1 element of the span of V1, V2 dot 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 Vj minus 1. But now all those elements have been thrown away from the B and the new list has been created where none of them has this dependence. So, which means that the given set cannot be linearly dependent, it has to be linearly independent. And since they span also the vector space, they form a basis. So, here the idea may not be so easy to understand, but let me just try with you again. You needed have to read it to try through it, because what it says that check whether V1 equal to 0, because if there a 0 vector cannot be a part of linear independent sets. So, throw it out if it is 0, if not keep it. Look, take V2, is V2 linearly dependent or linearly is in the span of V1, is some lambda of V1. If it is, throw it out, if not keep it, and then check V3 and then go on like that. So, what would happen that the span of the final remaining vectors would be span of the original vectors, because what we have thrown out are also span among these vectors, are spanned by these vectors, right. So, now what we have learnt in linear dependence lemma is, if there is a set of vectors V1, V2, Vm say which are linearly dependent, then there exists a J for which Vj is in the span of V1, V2 dot 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 Vj minus 1. But now in this new list that we have got through this algorithmic scheme, no vectors in that final list has this property that Vj is element of V1, V2 dot 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 Vj minus 1, right. For example, when I have V1, V2, I throw away V3 and then I have V4, then V4 now takes the place of V3 and then we have to check with V1, V2 again in that way. So, what happens? So, in the final list there is no such Vj which is in the span of this, because any such Vj has been already thrown out. So, by the linear dependence lemma, this set of vectors cannot be linearly dependent, because linear dependent means that this property has to be satisfied. So, there must be some j for which this property is satisfied. Here none of the j's for which this property is satisfied, and hence all these vectors are linearly independent, and because they span the whole space. So, this is a basis, right. So, every finite dimensional vector space must have a basis. So, that is obvious now, you can just figure it out. Now, we come to our second question, that if V1, V2, Vm be a linearly independent set in an n dimensional vector space V, and if m is less than equal to n, could be strictly less than n, then the set of V1, V2, Vm could be added with n minus m elements, so that the new set of n vectors is a basis of V. Now, W1, W2, Wn is a basis of V, and so these are linearly independent, it is a linearly independent set which spans V. Now, I create a new set B tilde, V1, V2, Vm and W1, W2, Wn. Now, these are all linearly dependent vectors, because any V1 can be expressed as a linear combination of W1, W2, Wn, because W1, W2, Wn is a basis of V. So, I can actually now say that this is a linearly independent set, right, they are not linearly dependent. This whole set is not linearly dependent. Individually V1, V2, Vm is linearly independent, W1, W2, Wn is linearly independent, but when taken together they form linearly dependent vectors. Now, apply the algorithmic approach in what we have just learned, the lemma 4.3. Now, you see V1, V2, Vm are linearly independent. V1 must be non-zero, because it is among the linearly independent set of vectors V1, V2, Vm. You take V2, V2 and V1 cannot be linearly dependent on each other, because then the whole V1, V2, Vm will become linearly dependent. So, when you throw out the vectors V1, V2, Vm cannot be thrown out from B tilde. So, anything that gets thrown out must be among W1, W2, Wn. And in fact, finally, you can throw out, because it is an n dimensional space, its basis must contain n elements, you can actually throw out n minus m vectors from this collection W1, W2, Wn. And as per the lemma, when you throw out these additional vectors, you will finally get a basis. So, basically you have put some elements here which are actually a basis along with V1, V2, Vm, and some of them are thrown out from here. Some W's are thrown out from here by the previous lemma, and what is remaining is the basis. You will finally reach a basis in which V1, V2, Vm is also taking a part. So, what we have done essentially, we have added some elements to V1, V2, Vm to make a new basis. I hope this is clear. This is a very simple game in town. So, now V is an n dimensional vector space, and any set of V1, V2, Vn of linearly independent vectors is a basis, because here my m is equal to n here. So, I have already made the extensions. So, I need not add anything else. So, and hence it will be a basis. So, I need not make any extension. Then, because n is equal to m, the number of elements that I need to add here to make a basis is 0, that is n minus m. So, lecture today, and hope you have a nice evening. Please feel free to ask any questions to me.